Okay, Year 11s, this is a diagram of a gas chromatography instrument, a very primitive one, but nonetheless. So here on the left-hand side, you've got where the gas bottle is of your inert gas that makes up the mobile phase, something such as helium or nitrogen gas. And it passes through some pipes and into the gas chromatography coil. It can be made of glass or something like that. And this coil is housed in an oven, and that's really important because the oven obviously is what generates the heat, and it's the heat that allows the analytes to enter into the gaseous phase and therefore be detected at the end. Speaking of detected at the end, this is the detector here, which essentially just collects the certain gases as they pass through and amplifies the readings, and those readings then come out on a piece of paper or stored in a computer. And this R stands for the recorder. This little purple box here is showing the injector, and that's where the very small amount of sample is injected into the gas chromatography coil. So that's a brief overview of what a gas chromatography instrument would set up like. And now we need to think about exactly how it is that gas chromatography allows us to analyse our certain materials. So gas chromatography is well suited to the analysis of things that are reasonably volatile and that can enter into the gaseous phase without too much difficulty. So they're quite common in the analysis of drugs and alcohol in the blood, for example. Now, as I already mentioned, the mobile phase in gas chromatography is some kind of inert gas, and helium is quite a common one, and nitrogen also. And the stationary phase in gas chromatography can either be a liquid or a solid. And if you're using a liquid, then you have to make sure that it's the liquid itself isn't volatile, because you don't want a situation where you're heating up your coil and your stationary phase, the liquid, turns into a gas. Okay, that would be a nightmare because you'll end up with a reading for that, and it might hamper how you read out the rest of your gases that are passing through. As mentioned, can also have a solid, something such as silicon dioxide, for example, would be a suitable solid for gas chromatography. So now that we've sort of sorted out what our respective phases are, let's just consider how it is that this method actually can work in the detection of our analytes. So let's just say that these two parallel lines here represent the column through which the analytes are going to pass through, or the coil. And this coil's in an oven, remember, and the temperature can be manipulated. Now, on the outside here, you've got the sort of outside of the column, and then here, this would be this is the liquid phase or the stationary phase, and that's made up of a viscous kind of a liquid. The idea is that your inert gas or your mobile phase is passing through here like this, so the direction is from left to right, and I'll just mark that as helium, but any other appropriate mobile phase would also work. And if you have these, actually I probably should do that in a different colour, bear with me, there we go. Some gases will or some liquids that get injected that you're analysing will have a tendency to just remain more in the stationary phase than they do in the mobile phase. And some of them will go ahead and enter into the gaseous phase very easily. And so that would be these ones here. Okay, there's more of them in the mobile phase and less of them here in the liquid in the stationary phase. Now, it's this pattern here that's very important when you're considering what's what. So it's these ones here that are in the mobile phase that enter in really easily. They're your more volatile substances. So they have lower boiling points because they've entered into the gaseous phase at a temperature much lower than these ones. It also tells you not only information about the boiling point, but the fact that there's not a great affinity of these molecules for the stationary phase. So they're not very soluble in the stationary phase. The ones on the left-hand side, these ones, they are almost the complete opposite to this. So these ones here are much less volatile. Their boiling point is more because they're more inclined to stay in the liquid phase rather than the gaseous phase. And they're also more soluble in the stationary phase because that's where you're finding more of the molecules. And they're less inclined to enter into the gaseous phase and move along as they get swept up by the helium. So that's sort of how the gas chromatography allows you to separate out your different substances, for example. Now, what happens at the end of your gas chromatography is that you get a printout of your data, and it can be shown on a graph that looks a bit like this. Now, the horizontal axis shows you retention time, and basically that means how long it's stayed in the coil for, how long it's stayed in the mobile phase. And this shows you sort of like relative abundance or amount, if you like. Now, the volatile substances that enter into the mobile phase with at much lower temperatures with ease, they have low retention time. So they're the ones that come out first. So they would be plotted down here at a time much less than these ones here. So these have a high retention time and they come out towards the end of the graph like this. And the amount of area that you've got underneath a peak will tell you the relative abundance or how much of it. So the gas chromatography, the printout will tell you two things, okay, how much you've got of this substance and what its retention time is. So a plot for what we've got above might look something like this. So the square molecules are represented by this peak because they're more volatile and they've come out first, so the retention time is less, they spend less time in the coil. And our triangle molecules are this peak here because they've spent more time in the coil and their retention time is more. If you've got a lot of area underneath this peak, then that tells you the substance is fairly concentrated. If you have a very small area like this, then that tells you the substance is not very concentrated. It is possible, so let's say that this was a known standard of two substances, could be, say, something like a particular drug or alcohol. So if what's shown in orange is a known standard with a known retention time, then it's possible to run an unknown through that, and should an unknown peak come up, then you know that this substance here is also present in your patient's blood, let's say, or urine or something like that. The presence of the peak tells you the presence of the peak in the same spot tells you that that this substance is present. But note here on the yellow one, I've got less of it, so it's the area underneath that's telling you how abundant it is. It's also possible to plot a concentration calibration curve using gas chromatography analysis. So similar to your atomic absorption stuff, if you plotted a calibration curve and then you, let's say, run a blood sample for blood alcohol reading, for example, and you can then use your known standards to come up with a reading for concentration. So that's a little summary on gas chromatography, guys, and I hope it's helped you out. Thanks for listening.